All right, so we're going to talk about databases now, or at least data design. And the goal here is to we're going to start talking a little bit about uh, uh, file-oriented systems, because that's ultimately where databases kind of came from. And I know when I was a student, that was one of the things we had to do, is we had to go ahead and create our own database using this kind of technology. But then we're eventually going to move into the more relational world of, of of entities and attributes and all that kind of stuff. We will get into normalization, which hopefully you learned in a database course somewhere. Talk a little bit about codes. We'll talk more about data warehousing, data mining, and then trying to control access to data. So here we got data structures. So basically, when you think about programming, the variable is the smallest unit of data, but even in programming, we get data structures. We get the records, you get objects, you get tables. And although this may or may not be true, certainly what happens in databases is that a file or table will contain information about stuff that is interesting to your problem. So, people, places, things, or events. They're going to give sort of an example here of Mario and Danica. So Mario's auto shop uses a file-oriented system. And so the mechanic system uses the mechanic file to store data about the shop employees, and the shop system uses the job system, uses the job file to store data about work performed in the shop. Now, in this case, Danica's auto shop is different because it uses a relational model, and he uses his shop operation system. The tables are linked by a common field in the mechanics number field. So in Mario's shop, you can imagine there's sort of these two files sitting out there that are independent of each other, that are maintained separately through different programs. In Danica's auto shop, we're talking about basically, instead of having mechanic being a file, it's a table. Job is not a file, it's a table, and they are connected through this relationship. And we'll certainly be talking more about that in a few minutes. So file processing is still very much a thing, or at least, well, actually, I'll still say it's very much of a thing. Older systems for things like banks, Department of Defense, all that kind of stuff, they probably still use some concept of sort of a master file, which is a customer transaction file. They'll probably have logging files. They'll have work files. It's basically how the mainframe did things up until when the relational database, actually, I was going to say relational databases. There were databases before relational databases, but anyway, until the sort of enterprise databases started coming out, everything was done through files. But they were not particularly scalable, for one thing, and the other thing was that there's plenty of errors that could actually happen there. If I go back to this example, does this job connect? It must connect, right? There's a mechanic. So if this was just an independent file, there's nothing to stop me from throwing some jobs into this file that have no mechanic particularly involved with them, or making up a new mechanic number. A lot of my early career was trying to figure stuff like that out. So relational databases basically are, they have that advantage of basically linking things together at the database level, not so much the program level. So your acronym here, database management system, it's a collection of tools, features, and interfaces that enable users to manipulate and analyze their data. And they usually are quite scalable. Access, by the way, counts, and that's why I kind of go, oh, I don't know if it's scalable or not. But Access is definitely more scalable than doing the same thing through spreadsheets in Excel. All right, there is somebody usually in an enterprise-wide system that is in charge of the database, or at least the way it works, and that's the database administrator. And again, it's talking about some other things. You got standards. The database, relational databases are based off something called SQL, Structured Query Language, that is controlled by the ANSI people, the American National Standards Institute. Mostly, it doesn't stop, IBM and Microsoft from adding their own flavor to it. But when you look at ANSI SQL and compare it, you can see that it is kind of doing the same structure. They definitely can control security a lot easier, and they can also give people different levels of security inside. And what's really cool is that the systems that interact with the database are relatively independent by how the data is maintained. So the database itself has sort of got all that information about how the data is maintained encapsulated in it, and then there's an application that's written around it. So here we got our administrators, our users, and other systems all controlling, or at least trying to get access to the data or put data in through the database system, database management system. All right. So I brought up SQL before, and I don't know if I've missed it, but I haven't seen SQL pop up yet. But SQL is an important thing, and SQL can be broken down to different sort of different parts. And when you're putting data in and pulling data out, you're using some kind of data manipulation language. And for those of you that know what I'm talking about, we're talking here about the insert, the update, delete, and the merge. Another idea inside of here is that a database typically isn't just a giant room of folders. Typically, there are, I would call them sometimes user accounts or schemas, which are basically a collection of related tables. Now, the word schema gets used differently in different relational databases. Even the word database gets used differently in different relational databases. But I think it's fairly safe for you to kind of believe that if you had an account on a database, your account would be a schema. And you might have tables in there that are all related to one particular problem. Now, the ones I typically show off usually are things like the human resource schema, which is a subsection inside the database. It's got all the human resource tables in it. And then you've got the order entry schema. And even that's really quite simple. When I think of the databases I've had to work on, there's usually many schemas in there that try to capture the totality of what an object actually is. Like, for example, for a customer, I think the customer would be in one schema, but the customer could easily be 14 or 15 tables together that make up the idea of a customer. Okay, so that's what the schema is. It's talking here about a physical data repository. So I guess what they mean by this is the actual database itself. It's the collection of schemas and sub-schemas. Databases are now certainly well able to connect to the internet. I've got sort of something running right now over here. I'm using something called LiveSQL, but I'll return to it in a minute. But basically what this is this is a browser-based internet. Browser-based internet. Let's try it again. Browser-based database. This is an application which I've used to demonstrate a few things. This thing is obviously also accessing a database through a browser. All right, and super important is this concept of data security and try to ensure that the data going in and the data coming out is secure and yet still accessible. That problem hasn't gone away with the internet. All right, so the kind of, here's a little chart for you to sort of look down some characteristics, and I'll let you look at that on your own, but here's a nice little picture. So when I'm over here on my fabulous web database and I want select asterisks from employees, I don't know if you know any SQL at this point. You're not guaranteed to know any, so I'll just simply say that this is a very primitive piece of SQL. I'm basically saying select, so give me all the columns in the employees table. That's basically what I'm saying here. Yeah, I'm tempted to go more, but I won't. So what I did here is I went and made my request through the internet. It hit the web server. The web server and the database server are likely different machines. You hope that they are anyway. And so the web server made the request to the database shoots the answer back, and then the answer came to me. All right, so some definitions now. So we got the idea of an entity. An entity is like a person, a place, it's a thing, it's like a noun that you basically try to get information about. And an entity is usually made up of attributes. I'm skipping table for a second. Entity is made up of attributes. So I, for example, am an instructor entity. Actually, I'll go one step further. I'm an instance of an instructor entity. So you have an entity called instructor. Instructors have attributes, which is some single fact that explains me or describes me. So for example, I have a last name, I have a date of birth, I have a social security number. Those are all attributes. And then the entity will likely become a table. And a table will likely have columns or fields. And so that's kind of how these things kind of relate. So I would say over here that employees is a table and these are the columns. And yet at a diagram level, you could say that employees here is the entity and that these are attributes. It's all an issue of modeling, really, of looking at the logical versus physical layer. A tuple is a set of fields that describe one instance or occurrence of an entity. This thing here is a tuple. Now, or tuple, some people will say. Like, by the way, I guess grammatically tuple would make sense. I've always heard tuple though. But the point is this, nobody says tuple, but you may as well know it because you're going to get asked that question, right? But it's definitely more of an academic thing. I would say to you that this select statement returned at least 50 rows. I'd never say tuples. Now, this is important. When you're looking at this table here, you've got the concept of, we don't just have normal columns. These columns, some of them have special properties. This column uniquely identifies, what are you doing there? Stop that. Nobody wants to see me. All right, let's go back to that again. Are we good? No, we're good. All right. So anyway, so this table, this column, uniquely identifies the row. It has to be present because it uniquely identifies it. This is called a primary key. All right. Now, if there was a social security number in here and they all had one, that could have also uniquely identified the row. But if we're not using it as a primary key, that is a candidate key. Anything that can be used to serve as the primary key. Now, sometimes we don't like to use naturally occurring data as the unique identifier, because maybe it might happen one day that you end up with an employee without a social security number. I was in this country for 2 weeks without a social security number. So what we like to do typically is we like to put a value in its own column that uniquely identifies the row that really has no information in it whatsoever other than a number. Notice that in this case, the employee 100, 101, 102, there's no real information here other than that 102 is bigger than 101. This value, which is not on the slide, but you should probably know, this is also called a surrogate key. It's just basically a set of sequential numbers that uniquely identify a row. I would suggest to you that in Access, when you're using something called AutoNum, and I think that happens in SQL Server as well, those are also surrogate keys. They're used all over the place because even if this had a social security number, I'd be tempted not to use it as a primary key. It's typically a column created of sequential numbers that is made to identify a row. All right, so that is the primary candidate and the surrogate. Now, also in here, we have a neat thing where we've got this guy, department ID. What's department ID? Well, this is a number that points to the primary key of another table. And if I was actually to go click on my schema for a second, we'd see it, here's employees, here's departments. And I don't think, yeah. So there's department ID. It's the primary key for the departments table. So as I go back and probably destroy my session here, right, there we go, move me out of the way. What we're seeing here is department 90 is probably a department in the departments table. This is a key that if the value exists, points to the primary key of the departments table. Now, how do we know that at this point? Well, you don't, certainly not at this level in the course, but if you took a database course or whatever, you start to figure out that you can actually ask the database questions and you can easily find out. You can find out a lot about all of these columns actually. But anyway, so this column is basically pointing to department 90 in the departments table. what is going to happen is you're going to look up the definition of a foreign key, and you're going to keep hearing this constant thing about how it's a value that points to the primary key of another table. I really want you to internalize this point. Here's this guy, the manager of Nina is 100. 100 is actually king. The manager of Bruce here is 103. 103 is actually Alexander. This is also a foreign key, and it points to the primary key of a table, but not another table. So sure, on the tests and stuff, you may as well keep going with another table, but be aware that this is basically pointing to the primary key of a table, and also be aware that there's nothing in the logic that says that a foreign key must be populated. Primary keys certainly have to be populated, but not necessarily foreign keys. Foreign keys, it's if the value exists, it points to the primary key of another table. And although we don't see this here, and let me just do another quick peek at the schema to see if I can see a good instance of it. Yeah, job history. I'm going to go quickly and do the same query, but go against the job history. So job, and I think it was history with an underscore. Let's go and run it. All right. So what you're going to see here is that the employee ID isn't unique, but yet there is actually a key here. I just happen to know because I'm familiar with the data. These two columns together make the primary key, because what it's doing is it's tracking basically the start date of a guy's particular job. So we know, for example, 101 started as an accountant, left being an accountant, and then on the next row became a manager. And if we did a little bit more sleuthing, we'd see that they're actually moved on to become something else. So it's not that is unique. It is not that is unique. It is the combination of these two. And so because of that, that's where the secondary key is. It's a field or combination of fields that can be used to access records. All right, so this is all about referential integrity, and I'll quickly show that off for a second. Referential integrity. Let's go back and select asterisks from employees and go. And watch this. I'm going to go, and I'm just going to go delete from employees where the employee ID is equal to 100. I'm sorry for it all being in uppercase. I'm going to go. It's not going to let me. Why is it not going to let me? It's not going to let me because, let's go back to the worksheet. It's not going to let me because I can't delete employee 100 because there are people, I should say, reporting to employee 100. So if I just deleted 100, who would these people report to? It would freak out. The integrity between the two entities is compromised. If I was to say, hey, why don't we delete from departments where the department, oh my goodness, I'm spelling this out now. Hang on, it's been a long day. Department ID is equal to 90. So now what I want to do is I want to delete where the department is 90. Remember, I got people here reporting to 90. It's going to say you can't. All right, so that's kind of what I want you to get with referential integrity. It's the thing that binds two entities together. And in this case, what they're trying to say is, look, this table is related to this table through the mechanic number. Right? It's the primary key here, it's a foreign key there. Now, we can draw diagrams for this, and here they're using the Chen notation. Okay, Chen notation. And what we're going to do here is just talk a little bit about that. First of all, Chen notation, it's wonderful, but I would encourage you not to necessarily use that kind of notation because, quite honestly, it's not used a lot outside in industry. But it's going to be showing a lot of this in the book, so you may as well sort of see it. So here we got our entity, and our entity treats. So the doctor treats patients. Patients are treated by doctors. It's sort of a way to get the English part of your model together. And so here, an office manager heads an office. One office is headed by one manager. And you can kind of read the rest yourself. Now, entities are related to each other in three different ways. We're going to see one right now, which is a one-to-one, right, which more or less makes sense. Social Security is assigned to one person. One person is assigned one social security number. But we also usually have one-to-manys. A department can be employing, one department employs many employees. Many employees are employed by one department. Please understand, I'm not just doing this because I like hearing myself speak. Relationships are bi-directional. So they go from the left to the right and the right to the left. And you should be able to talk in English about each of these relationships. Okay, so this is a one-to-many. And then what's quite common is a many-to-many. So a student, many students enroll in many classes. Many classes have many students, and that's kind of what the case is certainly in our college, right? And so what happens here is that we end up putting in there some kind of associative entity. The registration entity is the thing that will control which student is in which class. And I really do spend a lot of time talking about that in my little inspirational video on this chapter. So definitely look that up. And so here is a fairly complete model of a bunch of relationships. So one sales rep serves many customers. The customer, one customer will place many orders. The order may list, or many orders list many products. Many products are listed in many orders. And one warehouse stores many products. Many products are stored in one warehouse. Now, I'll tell you honestly, we don't typically use, as I say, the Chen notation. A lot of times we use something called crow feet notation, which is what this is. And it's called crow feet because that looks like a little crow's foot. All right, but you can kind of see one-to-one, one-to-many, zero-to-many, zero-to-one. Now, when you're walking around your IT shops and you look at your database, your DBAs and your developers, they'll have diagrams up maybe on the cubicle walls, or maybe these things will be in common documentary folders, and basically the deal here is that you can get to see how these entities are related together, because you as a developer especially need to know how they're related. And so here they've given the same notation, but this time using crow feet. All right, this is almost like something you would see in industry. They're making special notes on these guys because these guys are the associative entities, right? This checkout list, it's got one user is on many checkout lists, and ultimately, I guess one book is on many checkout lists if you follow the path. So this checkout list associates the many-to-many between book checkout and user. So there's a quick discussion on normalization, and honestly, normalization can go pretty deep. In this case, what we're going to do is just go through an example which has an unnormalized design right up to third normal form. But the key here is understanding that a lot of data comes in pretty fluid, and normalization kind of brings it to a structure that makes it more referentially integratable. What a horrible word that is, but basically tries to minimize errors that are prone in a non-normalized database or design. So let me, okay, I guess first, sorry, we're going to see the standard format. This is actually not a bad way to write out a table if you had to do this in shorthand. Give the name of the table, underscore the primary key, and then the other fields. But first, let's just look at this. Here's a good example. So this spreadsheet is not normalized at all. There is not one thing that uniquely identifies the row. Now, your brains are filling in the gap here. Your brain knows that this line probably has these values in it. But notice, even if we filled in the gap here with 86223, and we just kept filling that in, and filled in here 86390, we no longer have anything that uniquely identifies a row, except perhaps by making a giant collection of fields. So this is not normalized. So the first thing we got to do is, and I guess what they did do is they basically combined, they filled in all the gaps, and then basically combined these guys to make the primary key. So now every row can be identified Now we actually have it in first normal form. No repeating groups. Second normal form is when you start getting rid of something called functional dependence. So it's saying here that field A is dependent on field B if the value of field B depends, field A, sorry, depends on field B. So what they're saying here, let's go back to this guy. So I've gone back looking at first normal form. And what I'd say to you guys is that the supplier name is not dependent on this order or even the product. The supplier name is dependent on the supplier number. The supplier name is functionally dependent on supplier number. I would say the same thing with the product description. Blue Gadget is not dependent on this combination of keys, it's dependent on the product number. So this guy, Blue Gadget, the description is functionally dependent on the product number. There should be at least 3 entities here, because what we've got is we've got one entity that is describing the order, something that's describing a product, and something that's describing a supplier. And what you see back over here is that that's what they've done. The order number, sorry, the order becomes basically this idea of, oh, I see what they did there. Oh, that's interesting. Okay, one second. Anyway, I'm caught up. The order is basically information that's only describing the order, which in this case is the date. The order line has got everything that describes the order line. And then product is a little denormalized because supplier should come out of that too, I think. But basically, in this case, these things all describe the product. Yeah, I totally would have removed supplier name from that. Now, third normal form is when you try to get rid of things that can be derived, like things that can be derived. So boy, do I not like that example, because what they did is they basically said, hey, supplier name should be pulled out, and that's what makes it third normal form? Really? That's what you're going to do? All right. Yeah, we're not going to do that. So just give me a second here. I'm going to look up another quick example for us. All right, I was trying to be a good soldier and use the example in the book, but I did not like what they did with the third normal form. So I'm going to just do this one instead. So what I've got here is, again, I've taken a step back. What we're looking at here is a departmental report, which has got basically departments, department names, manager, who manages that department, what's the job title of the person, and then it's moving over there. And then what's the hire date, salary, seniority, and yearly salary. Now, first of all, we see repeating groups, right? We see, for example, this group here repeats for this value. So the first thing we need to do is basically get rid of repeating groups. So we did 2 things here. First thing I did is I got rid of the repeating groups, and then I've assigned a unique identifier to every single row. So every single row is got a unique identifier. Now, the next thing was, well, how do you get the second normal form? Well, this job title does not describe this employee. What describes the employee is the job ID. The job title describes the job ID. Department name doesn't describe the employee, it describes the department. Department name describes the department ID. So what we got to do then, our next step is to split those out. Now I'm using colors to separate different tables. So in this case, the white and the yellow basically are one table, and then the blue is one table, and the green is another table. This is now in second normal form. But now the key part here is, what about third normal form? Well, this data is still not super secure here, because what I could do, my yearly salary is the monthly salary multiplied by 12. Now, what happens if I decide to change the monthly salary here? All of a sudden now, this is wrong, right? The integrity of the data isn't keeping up with this. This should be like 520,000 or something like that. That's what that should be. But it's not, because it didn't follow a calculation through. This is derived data, and I shouldn't store it on my table. If I know what the salary is, I can ask, as I'm pulling information out of my database, what is that multiplied by 12? But I shouldn't store it in there. A classic example of this, by the way, happens all the time in doctors' offices. I have to fill out, usually on the same form, today's date, my date of birth, and my age. Now, how does that make sense? Because if you know my age and you know the date, you have a good guess on my date of birth. If you know the date and you know the date of birth, you definitely can work out what my age is. Why do you need all three? And I've always been tempted at some point to screw that up by basically putting my age as 12 or something like that and seeing if they could figure that out, because someone's entering this data, and I often wonder, do they ever work that out? So anyway, so this is derived. The other one that's derived is this one. And by the way, apologies, because I'm sure it's not right, but the seniority is basically how long ago the hire date was. And this guy's seniority, if he really was 2003, would be much more than 9. But again, this is using two things. It's using the date and the hire date to give me a number. And so that's also derived data. So the next thing I do is I basically pull those things out. And that's basically third normal form. Third normal form would be taking this report, or really realistically this report, and splitting up so that we have departments, employees, and we have jobs. And that's kind of what I was trying to say in that little slide there with normalization. So I'm not sure, again, I agree with how they did it there, but that's how I do it. All right, and so now it trying to gives you some real world examples. So here's our student denormalized. First thing we do is we basically slap on, and again, they made a massive composite key. I wouldn't do that. I'd put the surrogate key on it, but whatever. Then they go ahead and they split it up, because back here we've got things like the, well, certainly the advisor thing should get pulled out for sure. And is that what they did? They got the student here, they got the course here. Oh yeah, the number of credit hours is per course. And then there's the grade. That's now it's second normal form, and then they basically start peeling off. Again, they seem to keep doing the snowflaking idea, but anyway, whatever. All right, I'm done with those. Let's just move on. Last thing they're going to talk about a little bit here is the codes and the idea of using codes. I'll let you read that. That's not really a big deal for me. Okay, and then we're on to data storage. So data warehouse. All right, so here's what I want you to understand about a data warehouse. If you end up in a situation where you've got a lot of data coming in, and it doesn't even have to be a lot of data anymore, like even like a chiropractor's office will have enough data for a data warehouse. What you do is your data is usually in highly normalized forms, so highly normalized tables. And a lot of times what people need is they need to run queries, and they can't run these queries on especially millions or perhaps tens of millions of rows if the data is highly normalized. And I guess at this level, I'll just simply say it's because in theory you don't know anything about joins or any of that kind of stuff. It's just very computationally intense. So what happens is that people like me come along and basically take data from source systems and pull them in to a data warehouse and basically convert it, or in fact, actually what we do is we extract, transform, and load it into a data warehouse. Typically in the format that we think will be much more easily digestible by the system. So for example, in a chiropractor's office, what would they be interested in? They would probably be interested in who are their patients. So we'd want to be able to take all that data and slice it up by patient. They would definitely be interested in time periods, like how many patients we're seeing that month, by what chiropractor. That would sort of be a nice sort of way to split the data up. The data might not exist very easily in that form in its initial state. What we do is we take data, we extract it, transform it, and then load it into a format that can basically live in this warehouse. Yeah, that's all they're going to give us. Huh? Well, anyway, so definitely look that one up, and hopefully in your database classes you got a little bit more conversations on that. But yeah, I guess actually you're getting a lot here. Here's your source systems. Here's the sales input, the human resource input, and it gets mushed together into sort of facts and dimensions. So here they're giving you some idea of dimensions, like everything you ever want to know about the sales rep, everything you want to know about the customer, everything you want to know about the time, and then in here would be probably, you know, let's say one table, which basically had a foreign key pointing to this dimension, a foreign key to this dimension, a foreign key to this dimension, and then itself a primary key, and that's how the data would be split up. If you truly are interested in any of this stuff, I can definitely go deeper. So let me know. And when it comes to data mining came after data warehousing. So data warehousing, you typically know what your questions are. Like, for example, how many patients did I see? In data mining, you don't necessarily know what your questions are. Data mining is your ability to take a bunch of data and look for interesting new patterns. So, for example, a chiropractor might pull all their data into a data mining application, push the go button, and out would come a pattern that would say, for example, on Thursdays at the end of the month, you tend to get more patients than any other time. Now, the chiropractor didn't ask the question like, you know, how many patients am I seeing on Thursday? That would be a data warehousing question. But the chiropractor would say, are there any interesting patterns in my data? And that would pop out. All of a sudden, you get a spike in activity on Thursdays at the end of the month. Now, when I did an exercise like this, I took a bunch of climate data, a bunch of criminal data, criminal activity data, and a bunch of economic data. And I had it all broken down to the day level with a bunch of ups and downs. So was the economy going up? Was the economy going down? Was the temperature going up? Was the temperature going down? Was the criminal activity going up? Was the criminal activity going down? And I threw it all into basically this data mining application, and it spat out an interesting stat. Now, one interesting stat, which I'm sure you don't care about, is that apparently it gets warmer in the summer. The thing did actually figure out that pattern, which we were very excited at, but that wasn't actually an interesting pattern. But what was interesting is that on Fridays, when the weather is nice, the crime goes down. How about that? That was an interesting pattern. And that pattern could be actually used by police forces, because what they could do is they could start using that to determine their staffing. There's some other instances too of this happening. You know, a fairly classic one is some pastry out there, by using data mining, came up with the interesting pattern that when it rains, they tend to sell more croissants than muffins. So on rainy days, they make more croissants and muffins. Another really interesting one for you guys is that there was a data mining thing down at a grocery store where it made the discovery that men were more likely on weekends to buy beer and diapers together. An interesting pattern. That would be really difficult to try and figure that kind of stuff out if you didn't, if you're just trying to think like, what do men buy with or whatever. I mean, that'd be a different question, but they weren't going in for that question. They basically said, hey, give me some interesting patterns. And that was the pattern that it came up with. It basically said men are more likely on weekends to buy beer and diapers together. And so you guys are seeing data mining all the time, right? When you're on Netflix and it's making a suggestion as what movies you might like. Amazon, of course, was one of the leaders in this. So as far as book recommendations, what I'd like to see eventually in the colleges is data showing, you know, what students are more likely to drop classes, for example, or whatever. So in theory, you could jump in, get an alert, and say, hey, this student is likely to drop your class. You might want to see what's going on, right? So anyway, so that's what data mining is about. All right, and I think I'm definitely not going to talk about any of that because we talked already too long. Yeah. Oh, I should talk about backups a little bit. So databases typically need to be backed up, and there's a variety of ways to do that. And in a high-level database course, you probably learn that you could basically back them up. A total backup, you know, what's called a cold backup, that's where you shut down the database and do a backup. You can do a hot backup, and even when you're doing your backups, you can do incremental backups, you can do full backups, you can do temporal backups, you know, based on certain times. The database themselves typically are auditing as they're going along. So sometimes when a database crashes, it's actually smart enough to recover itself to the moment just before the crash, because it's remembering all of its stuff in audit fields. Databases typically have a level of security, usually role-based security, where what you can do is control who can get access to what objects and who can do certain things to what objects. So there's a lot of really cool stuff with databases, and really this course, this particular chapter was really just meant as a primer to that. All right, that was nice and exhausting. So that's all I got for you on databases, and what we'll be talking about next is the actual assignment.